So we left off yesterday starting to look at the cell. We first just talked about reactivity, and that's just important to remember that the metal that's by itself has to be more, if it's more active than the one as an ion, then they switch places. Okay? If they don't switch places like this one, that means that the one that's an ion is more active than the metal. The ion's always a pair. It's in a partnership with something else. That's why it dissolved, or how it was able to dissolve. Then we jump down here, and I believe we got this far. We read this. It told us that the electrons flow from PV to the X. It's important to write. If you know the flow, you're understanding a lot of what's happening. And then it asked for letter B. It said write the equation for the half-life that occurs at the anode. And when I look at this, is this gaining or losing an electron? It's an important question to answer. Is that gaining or losing? That is losing. So this is oil of the oil ring. So this is oxidation. And at an anode, it's N-ox, anode oxidation, right? Reduction cathode. Okay, that's where we left off. So letter C, it said the value of the standard potential for the cell is 0.47 volts. Just so you physically do this once. This will usually be given to you, but sometimes it's literally written in the voltmeter. So just understand that that's where you could see it. I would just write it up there. You might actually just have a recollection that that was there. That could be a hint of where you get it from. But that's 0.47. Determine the standard reduction potential. In reduction potential is always reduction, rig. Reduction involves gain. For the half reaction that occurs at the cathode. Okay, so here's where I have to give a little bit of a disclaimer. In the past, you would have had a sheet, I can do this up and have it out, that was on the back of the periodic table, and it was the reduction potential values. The problem was every single problem you were kind of like, do I have to use it? Now they will give them to you within the problem, so it's a huge hint. So what I'd like you to do, write this on the side or somewhere. This would have to have been given to you somehow. That's exactly the way it would have been written. This is not something that you have to know. I always just smile when someone's like, do I have to memorize this stuff?
Do they do that for enthalpies too? For bonding?
No, that's a great question. No, they will always hint on that, and that's really nice. If all of a sudden it's like, hey, here's some enthalpies. Okay, now I can get my mind set on this, like what's happening. Good question. Although, with an enthalpy, sometimes they'll give you all the enthalpies except for like O2 or H2, and then you're like, they didn't give me one. Well, an enthalpy for a pure element would be 0. So you would have a little connection on that. Okay, so they give this to you, and then they tell you that the overall cell is 0.47 volts. So let's talk about how that breaks down. More or less, there's other ways to teach this and learn about it, but you have two voltages from your anode and your cathode, and they have to add up. And they were going to add up to 0.47. So you do have to interpret this because nothing's going to jump out of the way to give you a sign that you did this wrong. This is what would be given to you. Okay? Is there anything wrong with that right now? Looking at, and the problem is that we started this yesterday, so we're a little removed from where we were. So think about what we've done in the past on this problem already. All right, it is flipped, right? Look, this is what's happening. And you got to understand that it's losing electrons. You see the flow right there, right? The electrons are being lost. This says it's gaining it. Every time you're given voltages, it's called a reduction potential. They always give it to you in terms of reducing, which is gaining. That's losing, so that's oxidation. So what happens, guys, is that this gets flipped. So what is the final voltage then? It'll be 0.34, right? So that's how you figured it out. And now it's just one point. I must have recycled the answer key last hour. I was getting ready for my sub. So that's one point. It's fine. I'll wing it. Double I. Determine the identity of metal. Okay, now, you got to understand this is antiquated. This is old now. This is not referring to this. But if you did have a sheet like that, Ben, what is the one? You would just look it up. What is the one that has 0.34? What metal?
Copper.
Copper. That's as simple as that was supposed to be. So whatever voltage this is, it just links to something. So maybe they would give you a list, or maybe they probably have to ask this question a little bit differently. So you just need to understand there isn't a lot to say about this. It's just whatever came up with this. Now, I wonder, is there a 60? Is there a 0.60? Or not? No. I was wondering if you put a negative here, you know, then you need a 0.6 to make that, and I wondered if there would be a different answer there. So you could have actually had a, like, well, wait a minute, a moment of, there isn't one that has that answer. Maybe I did that other part wrong. And you could have went back. But that's all that one goes with. All right, letter D. Describe what happens to the mass of each electrode in, as the cell operates. All right, we have worked on this. You need to think about what's physically happening in these. Now, I'm not saying this is what's happening, but if you can recall this, whenever the electrode would lose mass, we kind of made it smaller, and when it gained mass, we kind of made it furry, which is called electroplating. That's what happens with like silverware and things. So, what you need to do is there's two ways you can do it. You can look at the diagram, or you can look at truly the equation. You can truly look at this equation. This is the half reaction of the Pb2+. By the way, the other one is a reduction, so it would have been this, just FYI. That's the other half reaction. Just look at the equation. Who's losing mass? Meaning, you're going from the mass of the actual solid metal. I try not to give this away, but I'm probably giving too many hints. Which one is losing mass? So look at the before and the after reaction arrows.
So the PV would be losing mass?
Why?
Because the electrons are like going away.
Electrons going away, and what's happening to Pb? That's the part. Going into solution, right? So this Pb is going into solution, so this has to be getting smaller, right? This is going from an ion to a metal. So this ion is plating onto the electrode. Does that make sense? Like, that's not about memorizing them. Like, you can memorize it. Okay, so an anode always loses and a cathode always gains. You can think about a fat cat. Could work. But you start putting in the animals too much, and next thing you know, you're like, I think there was a dog and a sloth. So you do need to say something. What I would just say is the Pb loses mass, and the Cu gains. I apologize, but I'm assuming that's 1 point. It's not like, oh, you got 2 for saying 1 of each. Well, you have some understanding, you're probably either going to get it or not. All right, stay with me. Okay, here we go. Last ones, and this one actually, it's nice. This is why I picked this actually, is because of the ending. It's a nice little conversation about electrochem. During the lab, students set up the electrochemical cell shown above. For each of the following 3 scenarios, choose the correct value of the cell voltage and justify your answer. So this is fully at 1 point, each one, by the way. You cannot get wrapped up in, oh my gosh, what if I don't explain this right, or if I get the right answer but not the right explanation? Just give it a shot. Don't over-explain. If you're not sure what it is, don't say things you don't know. Then just say, well, it's this, and that would affect that or make that decrease. If you don't know. Don't start saying things you don't, because if you say something wrong, you're wrong. I always just use the example. I say the correct thing, pigs fly, correct things. I gotta take something off. All right, a student bumps the cell setup, resulting in the salt bridge losing contact with the solution in the cathode compartment. Is the voltage equal to 0.47 or equal to 0? So the salt bridge basically falls off. What happens? You only got 2 choices. So first off, the voltage equals, what do you think? I think the number is not hard. I think the explanation is. What's it going to be? It's going to be 0. You need a salt bridge. You need a salt bridge. Think of it this way, you take something off the picture, the battery's probably not gonna work, right? Just, oh hey, let's take this off and this off, and this, well, okay, it's still working. It's not gonna work like that. Okay, now, let's talk about this because this comes up regularly. What is happening with this Selfridge? Sometimes they ask what actually happens in the Selfridge, by the way. If I'm doing PB, the 2 plus is going in, I'm getting too much positive in here, right? So what ion's gonna flow this way? The negative one, right? So if you're ever asked what is specifically happening in the Selfridge, the negative ion's floating, is traveling towards the lead cell, they'd say. And then here, this should make sense, the positive is leaving solution, so that means that the positive ion's floating that way. What are those ions doing? They're balancing out the charge, right? So this is what I would suggest. Keep it simple. There would be an imbalance in charge. It's the first thing I want to get across for you. And this is the second part. What's the biggest deal in all this? What is causing the voltage? What is the result because we have voltage? What is the most important part of all of redox and all this? What are we always ultimately coming back to and looking at? The electrons and the movement of the electrons. That's what electricity is. It's electron motion, movement. So if there's an imbalance in charge, eventually it won't allow for the transfer, for electron transfer. Let's just say that. This is the best way I can say it in the shortest amount of words, basically. That's the two things that are occurring. So the Selfridge, in general, is balancing out the charges. In general, if you're going to have a zero voltage, you don't have any more electron transfer. So that's kind of how I'm approaching it. Hey, this is what the Selfridge does, and if it's zero, that's what's happening in general. Well, that would be the result of it. It would stop really quickly. All of a sudden, you'd have all your negatives and all your positives, and there wouldn't be a natural flow of the electrons because they would already be overcharged one side and the other. Okay? That's just one point. After all that, still only one. Double I. A student spills a small amount of 0.5 molar Na2SO4 into the compartment with the PB electrode. I think this one's the hardest one, and we don't need to make it that hard. Resulting formation of the precipitate. So it makes precipitate. Why? PbSO4. Right. So what happens, I'll get there in a second. Is it less than 0.47 or is it going to be greater? So you're going to have greater voltage or you're going to have lower voltage. Justify your choice. Okay, don't just jump into it. Be a chemist. Think about it. So I am now having a solid down here. So what did I do? I reduced the concentration of this. You can, I'm going to explain this twice and act like I didn't explain it the other way. Let's look at it here. Here's my half reaction. What am I literally reducing? What goes down right now in here? What did I just reduce?
PB in solution.
So the PB2 plus?
Yeah.
Okay. Get out of your heads for a second. And if I just told you that I'm going to reduce the amount of this, what happens to the overall reaction? What does it do? Think about this. Don't think chapters now. Think in general, because you get stuck in chapters. If I reduce something on the right side here, where does the reaction go? It goes to the right. Le Chatelier is involved in everything. So it's going to drive it to the right. Just think about that for a second. If I'm driving to the right, what else is it producing? It's producing more electrons, right? So what happens to the voltage? Goes up. Okay, let's say I didn't explain that. Just, we'll write in a second. Don't write, please. If I lower this, this solution is less saturated. Okay, so if you don't want to attack it that way, what is happening here? The PB has to break off and go into here, right? So if there's more space for it to go, it can allow more of the PB to dissolve. And by doing that, it can continually even release more and more electrons because there's more space. It's less saturated. It's not as concrete, but that's another way you can kind of think about it. So either way, this is how I would write it though. Voltage would be greater than 0.47. And honestly, by lowering the concentration of Pb2 plus, like hit the heart of it. Like you can say this, the reaction drives towards the products. Hunter, give it to me again. What's the most important part of all this? Towards the products. Are you saying clouds?
No.
Oh, what are you saying? Electron what?
Electron flow.
A flow. Yes. Yes. Sorry. I didn't think you said it, but towards the products. That's how I would explain it. That's not exactly how they did it. They actually use an equation. Guys, we only have a couple minutes here, so. But this is great. This is exactly what you need to write. So I hope that makes sense. Again, if you're not sure, always go back to this. If they ever say, hey, I remove or add something to an equation, you got to at least entertain the idea of like, wait a minute, which way would the reaction go if I did that? Like, Le Chatelier can apply to everything. Okay, final one. This one's short. After the lab session is over, a student leaves the switch closed. The next day, the student opens the switch and reads the voltmeter. First, we got to make sure what it means to be closed. Is this, the lights are on right now, is that closed, or when I turn it off, is that closed? Those of you that are not in physics, this is something that you never talk about, but people think the other way, like, oh, it's closed, so it's off. No, now the circuit's open, and it's not able to complete the cycle, and it won't create that electricity. So if you're confused by that, by the way, the picture shows it. The switch is open. You're not actually having this flow yet. You close it, now you can have this flow. It's technically there. It's not up in the air. I mean, it's actually on that wire, okay? So if it's closed, it means it's running. Don't overthink this. I have a flashlight. I put a battery in it. I turn it on. I leave. I come back the next day. What's it going to be? Is it less than or equal to 0.47? That would be the grit. Be equal? You would be a billionaire if you made a battery. Think about that. If you made a battery that never, ever, it's like those watches that Eli Manning does. The Echo Drive or whatever. You not know it. It's like based on wrist movement and sun, so it like never dies. But you got to do this all the time. Hey, what's up? What time is it? I don't know. So it's going to be less. Now, honestly, it's probably 0, but we don't know that. It's probably 0 if it was all day. Like if it's dead. Now, please, when the electrons finally get to the other side, do you know what it means for a battery to be dead? Anybody know the actual phrase for it? Do you remember? When it's actually dead, what if, I'm going to give it away if I say one more word. But yes, I was going to say, what have we reached? So we can use that. As the cell operates, it reaches or moves towards equilibrium. I would actually write this then, ultimately reaching zero volts. Something like that. That's a point. Okay? So, some things that are good to discuss. Hope you can make it tomorrow. If you can't, I really hope that you're going to watch it and go over it before it. The reason and the why I picked from last, if you haven't looked at the last one too, the 2 review sessions, I go backwards and I try to pick some things that are all going to help in the long run for the final. Last thing on the final. Don't stress about how it's going to grade or how it's going to affect your grade. That's my job to worry about the reflection of what it all means. Just know this, that about 40% is a 3 on an AP Chem test. 40%. It's like a 40% is like a 75%. Something like that, right? So kind of keep that in perspective. You don't need to get a 90% on Sunday. Feel good about it. Also keep it in perspective that that's only half the final. The other half of the final only had 2 students ever not come out of it was something with an A on their grade, and those were really low because they chose to do nothing. People usually put good effort because you really enjoy the second part of the final. And you
Wait,
have
about like the project or something?
the project, the scavenger hunt, things like that. It's all fun. It's all good.
Oh, that's what the Twitter thing is.
If you need anything from me, please write me an email today. But I am heading home. I'm not going to be here. So maybe great weekend. I'm going to go clean up some carpeting and.
Wait, Mr. Gussie, so for the packet, there's no way I can get points for it?
Not for that one. So there's a lot of packets. I mean, when it's all said and done, you're stapling them all. So, well, you get points for working on the other part of it.